G'day gang, this is a question, an extension 1 question, semester 1, Barker 2012, and it's a it's actually a cracker of a question. So, I'll read it out. The radius of a sphere is increasing at the rate 6 centimeters per minute. So, I've got a bit Kerouac down here with the drawings, but I've just drawn this little sphere like it's almost like a balloon. It's a perfectly spherical balloon. Old mate down here is blowing air in, and the radius is increasing at 6 centimeters. I've buggered up over here. Seconds, that should be minutes. So 6 centimeters every minute. So it's not going up very quickly. What is the rate of increase of the volume of the sphere in cubic centimeters per minute when the radius is 3 centimeters? So what I've done here, the rate of increase with respect to time is 6 centimeters per minute. So that's dr dt, the rate that the radius is increasing with respect to time. So what we're going to do is, but we're after the rate of the volume of the sphere. So we're after dv dt, because that is the rate that the volume is increasing with respect to time. And a nifty little trick that we're going to use is something called the chain rule. And what that means is we're going to say, nice little purple here, dv dt is dr dt. So you're thinking, what? Where did this dr come from? What's going on with this dr? Get the dr out. So we've got to divide by dr to end up with what we've got on the left-hand side. So those dr's will cancel. And then we just pop dv there. So you can tell how these dr's will cancel out and you end up with dv dt, which is what we have on the left-hand side. And dr dt we've been given. We'll just substitute it in red. 6. And now what we need is an expression for this dv dr. So what I've done here, I've written out, this is the formula for the volume of a sphere. And the way I remember it is, like, which one's which. It's got a cubed here. Volumes are in centimeters cubed and things. So I just remember, 4/3 pi r cubed. That's the one with a cubed in it. So we've got an expression that links volume and radius. So what we're going to do is we're going to differentiate this volume formula with respect to r. We're going to get dv dr. So I'm differentiating here. Equals, and now this 3 comes down the front, so we're differentiating with respect to r. This 3 will come down the front, we're dividing by 3, so they'll go. And we get 4 pi r, and then we drop the power by 1 from 3 to 2. And the weird thing is, I've just realised this now, this 4 pi r squared, that's the formula for the surface area of the sphere. So that is really interesting, because you differentiate the volume formula, and you get the surface area formula. It's really weird when you think that Newton and Leibniz, the guys who invented calculus, were doing it to find like the tangents of curves and things, and it's just got this really weird property of nature with spheres. Anyway, I don't really know what that means, but maybe it's something you look into. Maths, so it's a funny old roundabout. So dv dr, we can just pop this in here. So for dv dr, I'll put it in yellow. So we've got that 4 pi r squared. That's just come from that dv dr. Now, what we're going to do, so 6 times 4 is just 24 pi r squared. Beautiful. So dv dt, so that's the rate that the volume is increasing as old mate's blowing the air in, is according to this formula. So you can see that it's contingent or dependent upon, it's not constant, it's dependent upon the radius at a point in time. So it says, what is the rate of increase, which is dv dt, when the radius is 3 centimeters? So let's chuck 3 in here when the radius is 3. So when r equals 3, so let's just do this little calculation down here. dv dt equals, so 24, so I'm going to chuck in 3 for the radius, so 3 squared will be 9. So it'll be 24 times 9 times pi. And you can just put that into your calculator, but because I'm too lazy to go reach for one, so the other side of the house, I'm just going to go 12 times 9 times 2 pi, because 12 times 2 is 24. 12 nines are 108. 108 times 2 times pi, and that's going to be 216 pi. 216 pi. And our units are centimeters per minute, because we're giving the radius in centimeters per minute. Oh no, it's not centimeters per minute, it's cubic centimeters per minute, because it's the volume that's increasing. So yeah, very careful to get your units right. So a cubic centimeter is a milliliter, so 216 times pi, so it's about 600 mils every minute are being poured into this balloon full of air by old mate down here blowing on the little air hose. And it didn't even say air hose, I just did it because I wanted to get a bit artistic. Alright, so 216 pi is the answer, so 216 is B. Beautiful. Alright, well, I hope that's clear. See you in the next video.